Hey guys, welcome to video 11 on thermodynamics. In this video, we're going to be taking a look at thermodynamic cycles. Now, at the end of the last video, I presented you the challenge of trying to come up with a cycle on your own, perhaps before actually taking a look at a cycle officially for the first time. And the main hallmark of a cycle that I pointed out was that the cycle starts at a point on the PV diagram and then returns to that same point through a series of different thermodynamic processes. So that's what we're going to focus on today in this video. So let's get into it. So to begin looking at thermodynamic cycles, we're actually going to take a look at a very simplified cycle so that we can learn the basic engine cycle analysis before we extrapolate it to something a little bit more complex. So an engine cycle for a constant mass is a shape on the PV diagram that is closed, right? So it's a closed figure, in other words. And so if we start at a certain location, say point A over here, through a series of processes, we will return to point A. And so we will create a closed figure on the diagram. So here is the cycle that we're going to be focusing on. It basically looks like a rectangle. And if you want to pause the video right now, you can try to name each of the processes and what happens, just to make sure that you are internalizing and understanding each kind of individual process. If you feel like you've already got that down or you're not ready to try on your own yet, let's just jump into it. And so we have an isochoric process here from A to B. Then we have a isobaric process from B to C. Another isochoric process from C to D, and then finally a last isobaric compression from D to A. Now, I've worked in a specific direction, and so we will put the arrows on the graph in this order, and that tells us something very specific that we're going to take a look at as we go through this. So let's just first talk about each process, and let's look at, for the beginning, focus on how much work is done during each process. So from A to B, there's no work done. It's an isochoric process. There's no area under that function. And then similarly for C to D, no work is done. So the work is done through the expansion from B to C and from the compression D to A. Now we're going to see, we have to start to look at what's the net amount of work done rather than just the work done during one process. But let's focus first on B to C. So we see we have a B to C cycle. The work done on the gas is negative in that case. And the D to A cycle, the work done on the gas, is positive in that case. And D to A has less work done than B to C. So if B to C has more area under its function all the way down to the volume axis, right, the horizontal axis, that would be the total amount of work done, right? And so we have that as a negative value, plus we have the work done from D to A as a positive value, okay, based on the sign conventions. And so if we have a larger negative value from B to C than we do a positive value from D to A, we have a total amount of work done on the gas that is negative, or a total work done by the gas that is positive. So we're just looking at it from those two different perspectives. So if you think about it, the net amount of work done, which would be the difference of those two, would be the area that shades in this closed figure. So we will say that for any engine cycle, the shaded in region, or the region that is bound by the processes, is the net work done. You can find each step individually and then try to overlap them, adding and subtracting, or you can use an integral that will follow that path and will allow you to calculate the enclosed area rather than just the area below that curve. So now that we've looked at the amount of work done during each process, let's try to figure out from A all the way back to A again through the cycle where heat moved. All right, so from A to B, we see that we have a pressure increase without a change in volume. And so with that happening, there's going to be a temperature increase as well. If we look at the ideal gas law, we see that pressure and temperature are directly proportional when volume is constant. Now, I'm not speaking about this throughout this cycle because I told you that we have a constant mass of gas. So we're going to say that the gas is not moving into or out of the system. So in this first section right here, in order for the pressure to increase and the temperature to increase, let's think about what maybe comes first. Well, in order for there to be a pressure increase, that means that we have to put some sort of energy into the system. Otherwise, the pressure can't just spontaneously increase. And so if we think about that, we would actually be adding heat to that during that process, which increases the pressure and the temperature. Conversely, from C to D, as we have no work done and the pressure drops, therefore the temperature drops, in order for those things to happen, heat must have been extracted from the gas. So we had a flow of heat out of the gas. Now, that increase and decrease in heat are not the only two places where this happens. Now, we are going to take a look at this when we have a little bit more understanding of entropy in the next two videos. But for right now, what we can say is that that's a very quick process that's happening because heat is moving into the system. The pressure and the temperature are increasing. We're looking at A to B here. And there isn't any volume change. And for that to be true, that means that it's happening very fast. So it's almost like an initial pump in of heat before anything happens. Then from B to C, we see that work is done, positive work is done by the gas, negative work is done on the gas, and there is an increase in volume, no change in pressure. So if there's an increase in volume, there has to be an increase in the temperature as well due to the ideal gas law if the pressure stays the same. And so in order for the pressure not to drop when there is an increase in volume, that would mean that there had to be, again, heat added to the system. So in A and B to C, heat is added into the system and flows into the system. So we've already stated that from C to D, we would have a heat move out of the gas as that pressure drops. And then from D to A, where we have an isobaric compression, that is a movement where we have a compression of the chamber, so it gets smaller, but the pressure stays the same. And in order for that to happen, the temperature has to drop, and therefore heat had to have flown out of the system, right? So heat's extracted from the gas in the D to A process in order for the pressure to stay the same. Now let's finally take a look at the internal energy, how it changes from B to C to D to A and back to B. So trying to analyze the changes in internal energy, we always remember that we have to look for what the main marker of internal energy is, and that is temperature. And so wherever the temperature increases, we'll have a positive delta U value, and wherever the temperature decreases, we would have a negative delta U value. So from A to B, we have an increase of pressure and heat is added to the gas. The temperature increases as well. There's no way for that temperature not to increase if the volume is staying constant. And so from A to B, I should have an increase in the internal energy of the gas. From B to C, at a constant pressure, as the volume expands and heat again is added to the gas, I should see again an increase in the internal energy. From C to D, I should see a drop in the internal energy. Another way to think about that, or to think about A to B, seeing as those are parallel processes, is that when heat flows out of the gas, we have a negative Q value. Work is zero, so delta U has to be negative as well from the first law of thermodynamics. So we have a negative value from C to D for delta U, and then from D to A, again, a negative value of delta U as we see a pressure drop, as we see a volume drop, and heat flows out of the system, we should see a decrease in internal energy. And so by getting back to point A again, where it's a specific macro state of the gas, I should be able to measure pressure, volume, and temperature as being the same at A, whether I've been through the cycle or not been through the cycle. And so I should see that the internal energy value is the same there. Now we are going to talk about, when we've discussed entropy, that there is a lot more to this as we run through the cycle. In other words, we can't get exactly what we started with. There will be losses that are unavoidable due to the nature of heat flow and the direction of heat flow. So we have to keep that in mind. So at this point, we're ready to look at the first law of thermodynamics for the full cycle. And we're going to just take one cycle, though it could repeat many times as it would in any real engine. But as we move from A back to A, we actually find that delta U, the internal energy for the entire system as a whole, is actually 0. We then see that we have a certain amount of work done, a net amount of work done on the gas, and then also how much heat was added and extracted from the gas. So what we want to think about here is that there was a heat flow into the gas over here. There was a heat flow into the gas over here. But then there was an exhaust over here and through this process over here. So what we're able to see here is that the net amount of work done, as we just described, would be the area bound by the thermodynamic processes A, B, B, C, C, D, and dA. And the net amount of heat moving into and out of the system, we would label in the following way. The heat coming into the system would be labeled as QH, because it's the high energy heat. And then as that energy is used to do work, we say that it's exhausted as low energy heat, which we label as Q sub C, or like cold heat, if you will. So now's a good time to introduce what we call the reservoir model, which is very similar to the PV diagram in the information that it contains, but it's very different in the way that the information is represented. So we see that we have something called a hot reservoir and something called a cold reservoir. And we've already established that heat will flow from a higher temperature to a lower temperature, and in so doing that will do work on the way. Now, in order to calculate the amount of work, we can look at it in two different ways. We could say how much heat I'm putting in minus how much heat is leaving the system would be equal to the amount of work that is done. So we oftentimes describe the efficiency of a cycle as the amount of work done per the amount of heat added to the system. We can also write it in this form because we've just established that work can be written as QH minus QC. So I can write QH minus QC over QH. And then by simplifying and splitting this fraction, I would have QH over QH, which is 1, minus QC over QH. So then it becomes apparent that if we want to increase our efficiency, if we can decrease QC, so if we can make QC a lower value, in other words, we have less exhaust heat, that would mean more heat is going from QH to work. Now, a lot of you might be thinking, oh, that would be so great if we could make all the work come from QH and none of it go towards QC. And then that would be 100% efficient because we would have that QC 0 and then 1 minus that would give me a value of 1 or 100% efficiency. And unfortunately, this is not possible. Now, people always say this is not possible because the second law of thermodynamics prohibits it. But remember, the law is named after the fact, right? It's an observation of our focus on the universe and movement of energy throughout the universe. So this is really the reason that this isn't possible is not because the second law exists. The second law exists because this is not possible. And the main reason is that you won't have heat flow from a hot reservoir to a cold reservoir if there's no cold reservoir, right? There would be no heat flow. So I think of it in terms of pressure differences. If there's no pressure difference, right, there will be no fluid motion. If there is no potential difference in electricity, there will be no electric field and thus no movement of charge. And so it's the same idea that this difference in the heat or in the temperatures from the hot reservoir to the low reservoir is the reason that the heat flows. And so if there is no low temperature reservoir and you can't exhaust any heat, then that means that nothing would be possible and we wouldn't have any work. So it's not possible to go from QH all the way just to W. There has to be some exhaust. The goal then would just be to have QC be as small as possible, and then we would have what is considered the most ideally efficient engine, which is called a Carnot engine. And we will look at that in the next video, a Carnot and an Otto cycle, and just to see how this could be achieved hypothetically. So far you might have noticed that all the arrows point clockwise in the example that we've been through in this video. But in fact, the arrows can also point counterclockwise. And when they do, it is no longer a heat engine, but actually the reciprocal, which is a refrigerator or a heat pump. And what that does is its main goal is to extract heat from the system. So considering the PV diagram, we see that more work was done during an expansion than was done during the compression. And therefore we had a net amount of work done by the gas that was positive and a net amount of work done on the gas that was negative. Now, if we switch the direction of the arrows, we can see that anything that was an expansion became a compression. And so the higher isobaric process in this simplified example would be the place where more work was done. So more work was done in a compression than it was done in an expansion. And this is basically how the refrigerator functions. It uses a compressor and it extracts heat. And so work has to be done on the system by external energy in order to force the heat flow from the low temperature reservoir to the high temperature reservoir. And you can think of the low temperature reservoir as being the interior of the refrigerator, and the high temperature reservoir being the back or the outside of the refrigerator, usually on the back of the refrigerator. And if you've ever moved your refrigerator and felt the back of it, I would highly recommend not touching it because it can be very, very hot, because that is where the hot is exhausting. And when that happens and we have a compressor, the compressor then turns the gas or the mixture back into a liquid, and the cycle can start over again. And so we can figure out the efficiency of the refrigerator in very similar ways to how we figured out the efficiency of the heat engine.